So now we will concentrate on methods of preparation of aldehydes and ketones. There are a number of processes. First of all, we will concentrate on formation by oxidation of alcohols. So I have already told you with the common oxidizing agent like KMNO4, K2CO2O7, CrO3, etc., chromium trioxide, etc. These are very strong oxidizing agents. Okay, but thing is that if you go for oxidizing a primary alcohol to aldehyde, and automatically it oxidizes to carboxylic acid group. So therefore primary alcohols, and to produce aldehydes particularly, you have to proceed from starting from primary alcohol, and but you cannot use this oxidizing agent. You have to prefer some other oxidizing agents, and if you go for using this oxidizing agents, you have to keep the temperature very much fixed. Can be only little bit more than 349 Kelvin. So therefore it is very difficult to maintain that temperature, and therefore we will go for using some other oxidizing agent. So here it can be used to, but it will automatically move to the next oxidation state, and you will end up with the product carboxylic acid group rather than aldehydes. Okay, so therefore we will prefer aldehydes and ketone formation, particularly aldehydes, by using this particular oxidizing agents like PCC. What is PCC? Pyridinium chlorochromate, Collins reagent, chromium trioxide, pyridinium, almost the same type of reagents. Okay, and also we can prefer copper at 573 Kelvin. Okay, so let us see this how this reaction proceeds. In this case, whatever we are using, whether it is primary alcohol or secondary alcohol, we will end up with only carbonyl compounds. It will not proceed to carboxylic acid. Okay, let us see the first reagent, that is Collins reagent. Collins reagent or chromium trioxide pyridine complex is a good oxidizing agent for conversion of primary alcohol to aldehydes. Additionally, an advantage of Collins reagent is that it helps to cease further oxidation of aldehydes to carboxylic acid group. However, the reaction with Collins reagent is possible in a non-aqueous medium such as dichloromethane. Okay. Now, how the mechanism goes? See, it is chromium trioxide, and it is having a complex with Cl and pyridinium. Okay, so this will the lone pairs on oxygen will first attack the chromium. One oxygen pi bond will break, and accordingly we will get a positive charge on oxygen, and then we will have two negative charges on oxygen of bonded to chromium. These two oxygens will have negative charge. Next is the proton transfer. The proton will get transferred to one of these oxygens. Okay, and it will become OH. Just see here, it is becoming OH. The proton has been transferred to this, and this negative charge in the next step will come and form a pi bond and allowing the Cl to leave. Okay, so this Cl will take one of the protons of the adjacent carbon and abstracting the proton and making a pi bond with oxygen, and this bond will break. So finally we will end up with an aldehyde. Next is, what is PCC? PCC is pyridinium chlorochromate, almost the same type of reagent. The mixture of pyridine along with chromium trioxide and HCl is in dichloromethane, leads to the formation of pyridinium chlorochromate or PCC. Okay, so here also we will end up with aldehyde. Let's see the mechanism. Almost the same type of mechanism, so you can go through it on your own. It's all the same. Now, formation of aldehydes and ketones by dehydration of alcohol by removal of water molecule, it can be done. So you go through all this writing. What happens in this mechanism is that we have used copper. This copper is the catalyst here, so it is acting just like a stage or a platform. The alcohol, see here what is written, it is ethanol absorbed, means the alcohol will get absorbed here. So accordingly the lone pairs on oxygen will act on it. It will be absorbed on the copper, and then one H will be leaving. Okay, so now next is what? Next is the H on this particular carbon, okay, will leave, and it will go as H plus, and therefore H plus and H minus will combine to form H2. Supposing at this stage you are getting one acetaldehyde, and in the next this one can react and it will give you a further substituted species. So for the present discussion, this part is enough, okay, that is showing you the formation of aldehyde. Next is, it can be prepared from hydrocarbons. Hydrocarbons in two different ways. One is ozonolysis of alkenes and another is by hydration of alkynes. Alkenes and alkynes, as you know, they have only carbon and hydrogen, so they have been called as hydrocarbons. Okay, let us first see ozonolysis of alkenes. Okay, how the reaction goes, we have done it previously also. This is ozone. It forms a pentagon, okay, we call it as monoozonide. Okay, then the bond breaks to form a oxygen minus, and the lone pair on oxygen is used to form a pi bond. Now this one being at a sigma bond, okay, this bond breaks and we get what is called is the carbon-carbon bond breaks. So the carbon-carbon form breaks, we get ozonide. Now the ozonide can further be reacted with hydrogen peroxide or zinc dust in water, okay, and the bond breaks to form the carbonyl compounds. Hydration of alkynes. Hydration of alkynes, it follows Markovnikov's rule. So where the A positive part will get added, where the negative part will get added. As you know, the positive part will get added to only that particular molecule, that particular carbon which has more number of hydrogens. So if you compare these two carbons, here there is H, here there is methyl, so more number of hydrogen is here. Not, there is no hydrogen bonded to this carbon, there is only a methyl bonded to this carbon. So the A positive part will go to this particular carbon, and therefore we are having a positive charge on this. The water molecule comes, and therefore the next water molecule will take the proton, making it neutral. We are getting here enol. This enol will then get tautomerize to form the carbonyl compound. So that's all for now. Thank you.